So here's a picture of the Mousetrap car that was constructed for the purposes of this experiment. The car was composed of a balsa wood body, 4 compact disc wheels, a Victor mousetrap apparatus attached at the top of the car, a wooden lever arm held in by a copper bar, ball bearings, 4 balloons that went around the wheels, and a piece of string. So we as a group noticed that a mousetrap car is an example of converting potential energy to kinetic energy. Here we have a visual representation of the mechanism of the mousetrap car. First, we start off with a string line winding from the drive axle. As the string unwinds, the lever arm moves forward, making the car roll. The mousetrap car uses the torque generated by the trap to spin an axle. This axle is attached to a set of wheels, and these wheels spin as well when the mousetrap releases its elastic potential energy. The spinning wheels drive the car forward along the ground, and while the car moves, there exists 2 types of potential energy, translational and rotational. Here's a video of the mousetrap car in motion. So now let's jump back to the idea of elastic potential energy. Elastic potential energy is the energy stored as a result of deformation of an elastic object. For example, the stretching of a string. In our case, it would be the elasticity of the different string lengths that were used. Elastic potential energy can be represented by this following equation. E sub E 1/2 Ke squared. K is the spring constant represented in newtons meters, E is extension represented in meters, and E sub E is elastic potential energy represented in joules. The purpose of this experiment is to observe how kinetic energy is affected by different string lengths. We will also note the effect of different winding angles as pictured above. The hypothesis was established to be the longer the length of string, the smaller amount of kinetic energy it will have. A shorter string will have a larger kinetic energy, and the bigger the winding extent, the greater the kinetic energy. Half of the extent should approximately be half of the kinetic energy, and so on. So here we have kinetic energy values that were calculated using the following equation. Ke equals 1/2 mass times velocity squared, with mass being a constant value of 0.195 kilograms. We see that from the experimental results, it confirms the hypothesis that the shorter the string length, the larger the kinetic energy. This happens because the shorter string results in a more compressed spring. However, the kinetic energy for different winding extent wasn't like what we expected. This could be due to human error while recording the motion.
Thank you for watching our presentation. We hope you enjoyed it. Bye.